Good afternoon, everyone. This is Mike Medoff, and welcome to our webinar this afternoon. So our topic today is meeting IEC 62443 requirements as it relates to cybersecurity threat modeling. And we're going to talk about the ARCHx tool, which is a tool that we use within exida to do such threat modeling. So we're going to go over the process of threat modeling, what our approach is to it, and how we do it, as this is a required item from the 62443 4-1 standard, which is the part of 62443 related to secure product development. So essentially developing products in a secure manner. The standard has requirements for threat modeling, but it doesn't really say how to do threat modeling. So you have different approaches that people take in doing this, and we'll go over our approach that we've come up with based on our experience, and we'll explain in more details how we do it, and try to give a real simple example. As within the time that we have today, we don't want to get into anything too complicated, but something that at least just illustrates the method. So in terms of introductions, once again, my name is Mike Medoff. I'm the Director of Cybersecurity Certification here at exida, and my email address is shown there. So if you have questions during the webinar today, there is a way to ask questions through the GoToWebinar software, and feel free to ask them at any time. If we see questions, we may stop and answer them if appropriate, or we may just keep moving and answer the questions at the end, but we will get to them all. I'm joined today by my colleague, Jeff Davis, and Jeff's email address is there as well. And I will be doing the introduction and talk about the threat modeling approach, and then Jeff will go through the simple example that I mentioned. So a few words on exida. If you're not familiar with us, exida is a company that focuses on functional safety and cybersecurity, and we help our customers achieve safe, reliable, and secure solutions through three main ways. We develop tools such as the ARCHx tool we're going to be talking about today. So tools that help you develop software and hardware safely and securely. And then we also do certification and assessment. We'll certify development of the processes that you are following, as well as specific products and systems and installations. And we also have personnel certifications. The CACE is for cybersecurity certification for engineers working on industrial automation and control systems. It's one that kind of focuses on cybersecurity, but specifically in that field. And then we have the well-known CFSE, Certified Functional Safety Expert, which will certify people to knowledge relating to functional safety. We also have comprehensive system lifecycle services where we can deploy experts to help solve your toughest problems in these areas. In terms of technical expertise, exida has authored most industry references for automation, safety, reliability, and cybersecurity. And we've researched and authored an industry data handbook on equipment failure rate data. That's a pretty important topic for functional safety, is trying to figure out how to use the right failure rate data. And we have spent a lot of time researching that and trying to come up with the best data to use for that. And we've authored the most comprehensive book on functional safety in the market. And as I mentioned, certification is a big part of our business. We're the industry leader in certification of personnel, products, systems, and processes to a number of different international standards and guidelines. So some of the main ones are shown here: 61508 and 61511 for functional safety, ISO 26262 for functional safety in automotive, and tool qualification for that standard as well. We've certified development tools like compilers and static analysis tools and integrated circuit lifecycle tools. And then for 62443, cybersecurity certification, and then machine safety certification, and then the personnel certification, as I mentioned, the CFSE and CACE. In terms of cybersecurity certification, we've been doing it for many years, about 10 years now. And so we actually started doing it before the 62443 standards were all completely out. And so to date, you can see we've done a majority of the certifications that have done by the ISA Security Institute. There's a number of organizations that can certify to that scheme, and we were the first to do that, and we've done the most over those 10 years. So ARCHx is the tool we're going to talk about. We're really mainly going to talk about the process that we go through to do threat analysis and threat modeling, but you need some way to basically document and organize and track what you're doing, because threat modeling is not something that you simply do one time and then you're done with it. It's an ongoing process that every time you update the software, you have to revisit the threat model. Periodically, at least, usually about once a year or so, you have to update your threat model, even if you don't make any changes. So the tool is a very important part of it. Having a way to really document and help drive the threat modeling process. So for this, we use the ARCHx tool, and essentially this is an integrated tool that does architectural analysis, and it's focused on supporting problem detection methods used for the design of products for functional safety and cybersecurity. So it helps you do failure analysis of hardware, of software, and then from a security point of view, help identify security threats or vulnerabilities. And so using this tool uses a common methodology for any combination of hardware, software, and custom ASICs or FPGAs. So just to step back a little bit, if you're not familiar with threat modeling, I wanted just to give an overview of what it is and why it's important. So threat modeling is essentially a form of security risk analysis or risk assessment for a product or system. And the goals are to identify security threats to that system. And so these threats are essentially potential attacks on that system, ways that someone could attack the system to either increase their authorization level in the system, or otherwise maybe impede or interfere with the system operation. And a key part of it of threat modeling is not only to identify the threats, but determine the risk of the threats. And the risks of the threats are important because you might not be able to address every threat that's possible, but if you can assign a risk, you can determine which ones are the highest risk and address those first, and try to address the most critical ones. Risk is generally determined by looking at the likelihood and consequences of a threat. And so from a cybersecurity point of view, when we look at likelihood, we usually look at how difficult is it to carry out such an attack. Is it something that needs a very sophisticated attacker, somebody who's very knowledgeable about the system, somebody who has a lot of resources and motivation? If so, then it's a difficult threat to carry out, and we say the likelihood is lower because there's just not as many people that have that amount of knowledge, resource, and motivation. But if it's a really easy attack that many people with limited skill set and limited amount of time and motivation could do the attack, then we say it's much more higher likelihood. In terms of consequences, really we want to just look at what is the impact of the threat if it's realized. If someone attacks and is successful, how does it impact the system? And we generally look at that from 3 points of view. How does it impact the confidentiality of the data in the system, the integrity of the system, or the availability of the system? Those are the 3 main aspects that an attack can usually interfere with. So the overall risk then becomes a combination of the likelihood and the consequences. So something that has a high likelihood and high consequences would obviously have the highest risk, and something with lower likelihoods or lower consequences would be lower on the scale. We also need to determine an acceptable level of risk. It's not really possible to eliminate all risks from a system, or at least not do so in a manner that's cost effective. So we need to determine what is acceptable, and we typically try to do this by looking at other risks that people accept in their everyday life, such as what's the risk of having an accident flying in an airplane. That's considered a pretty low risk. So we're trying to look for levels of risk that are kind of comparable to that. And then once we determine an acceptable level of risk, we essentially want to identify, compare the risk for each threat that we identify. And if it's below the acceptable level of risk, then we say this is acceptable. We don't need to do anything about this threat at this time. However, if it's above that level, then you need to do something to mitigate the risk or to lower the risks to get it within the acceptable level. As I mentioned in the beginning, the threat modeling is required by the 62443 Part 4-1, which is the part of the 62443 standard that talks about secure product development lifecycle requirements. So these are the requirements that you follow when you're developing a product or a system to try to make them secure by design or secure from the beginning. Today we see very often patching and updating systems to make them to fix security vulnerabilities, and 4-1 is all about trying to eliminate those vulnerabilities to begin with, so you don't have to patch them. And threat modeling is a very important part of that process. Obviously, if you can identify and eliminate threats before you even deploy the system, then you won't have to do it by patching the system later on. So the general approach to threat modeling is shown here. We essentially start out by creating a high-level description of the system. We usually call that the target of evaluation. It's the system that we're going to be evaluating from a threat point of view system, or it could be just a component or a product. And the description is important to make sure everybody understands what the system is supposed to do, what its functions are, and more importantly, what are the boundaries of the system. And then the next step is to create a context diagram, and that's where you clearly show how the system interacts with its environment. So you show all the interfaces of the system, all of the external that are external, and you show the actors or the external entities other entities that will be interfacing with that system. And this is very important because these interfaces to the system are essentially the attack surface for the system, which is essentially the paths that an attacker can use to get into the system. And so by understanding all of those interfaces and attack surfaces, that will help you to understand all the threats. If you miss one or don't realize that there's a certain interface or don't analyze it, then you could miss some key threats associated with that interface. Then the next step is you're going to document and analyze details to identify threats. And so this is probably the most critical part of threat modeling, is coming up with the threats to the system. And there's a number of different ways that you can do this, and we recommend that you try multiple different ways. And so we're going to talk about what those different ways are. Each of those ways kind of gives you a different view of the system, if you will, and allows you to think of different types of attacks based on those views that you're looking at. Once you've identified the threats, you want to assign risks to them, and then you want to make sure you have a minimal acceptable risk defined for your system. And that's something that could change over time. When you first develop a system, or if you have an existing system, you may accept higher risks in the beginning, but try to continuously improve that system so that you eliminate more and more risk over time. So you're going to want to, once you've established that minimal acceptable risk, you're going to want to mitigate all the threats that are above that level, such that you've mitigated their risk to be below that level. There are many different approaches you can take to identifying threats, as I mentioned. A key aspect is you could have a look at the system top-down versus bottom-up view of the system. The bottom-up view is commonly done, and that's where you would essentially look at the most common technique is to look at a data flow diagram associated with the system. So you essentially take all of those interfaces in the context diagram and then show how data flows within the system and between systems and where data is stored within the system. And based on that diagram of the system, you can then look at each aspect that's documented in that diagram, which would include data stores where data is stored internally in the system, data flows, which show how data flows to different parts of the system, and processes, which is where some sort of processing occurs on that data. And you would look at each of those entities and try to figure out how they could potentially be attacked. And so one common way is to use the confidentiality, integrity, availability that we talked about earlier, and look at ways that they can be compromised based on looking at all of those components. Another method is called the STRIDE model, where you look at different attack methods, such as spoofing, tampering, information disclosure, etc. And we'll talk about those in a little more detail as we go forward. So that's kind of the bottom up method, and the top down maybe is looking at different aspects of the system. And so as you can see here, there's different sources you can use. So use cases is more of a top down approach, where you look at what are the ways that someone uses the system or is expected to use the system. And systems will generally have many different use cases that are expected and the system is designed to handle. Well, by analyzing the specific use cases, it often becomes obvious, or often helps you think of ways that someone can misuse the system. And misuse could be accidental misuse, where they just don't understand how the system works completely and it's not intentional, or it could be intentional misuse, which we often call abuse. And so we have the concept of abuse cases also, where somebody's specifically trying to misuse the system to try to find and take advantage of weaknesses in the system. So that's one approach is by looking at the use case and identifying misuse and abuse cases, you essentially are identifying threats at that point. Data flow diagrams we've talked about as the bottom-up method. Another common method that's used is to look at the assets in the system. Assets in the system are essentially anything that would have value to an attacker. So an asset might be the configuration of a system, or it might be specific data that provides key information about users, like, for example, usernames in the system. And so by identifying all the assets in the system, you can then try to figure out which of those have value to an attacker and what potentially an attacker could do with those different assets to take advantage of weaknesses in the system. So that's one approach that's often commonly used. For each asset, you would try to look at not only what can be done, but how that asset can be accessed in the system. What are the paths to get to that access? Another view is to look at the actors or the threat agents. What are the types of people that might be interacting with the system normally, and what would be the types of people that might want to interact with the system negatively and might want to take advantage or hack the system. And if you understand what those people are and what their motivations might be, for example, it might be a disgruntled employee or a former employee, or it could be a competitor, or it could be a terrorist of some kind. So if you can kind of go through that and understand what the different motivations are of these actors and threat agents, then you can essentially a way to help you think of additional types of attacks on the system. Another thing to look at is the physical interfaces. So if you have a clear definition of what are all the physical interfaces, that the system can be accessed, this will help you think of potential ways that they can be bypassed. And another way that people don't often think about is to look at the assumptions of a system. When the developers are creating a system, they often make assumptions about how it will be used, what the environment will be like that it will be used in, and things along those lines. And sometimes those assumptions are thought out and considered. Often they're just things, though, that might be in the back of the developers' minds. So it's very important to try to make sure you understand what these assumptions are and document what assumptions you're thinking about when you're developing a system. Because if any of these assumptions don't end up holding true, that could end up being a threat or a weakness to the system. So that's another key point to look at and way to identify threats. So it's our recommendation that you go through multiple sources when you're trying to identify threats, because as I was describing, as you look at each of these different types of sources, you may identify different types of threats because you essentially have a different point of view. So then once you've identified the threats, as we talked about, there is a risk assignment process. And for vulnerabilities, risks are often categorized by using a CVSS score. And so anytime a vulnerability is disclosed about a product, usually you'll see a CVSS score. It's a number from 1 to 10, but then that number essentially gets broken down into categories of low, medium, high, or critical based on that number. So the CVSS score is a very quantitative way of trying to calculate the risk or severity associated with a vulnerability. And that could be used for threat modeling, although generally our feeling is that during threat modeling, you don't need to go to that level of depth. And so instead, we recommend just using a simpler method where you classify the likelihood of the threat as low, medium, or high based on how difficult the threat is to carry out, and then the consequence as low, medium, or high based on what is affected by it. And if you look at then a table such as the one shown here, you could figure out the overall risk based on the likelihood and consequence. So as you can see here, if you had something that was a really high consequence, but it was only a low likelihood, it would be, as you would expect, a medium level threat. So I think this level of granularity is usually good enough for threat modeling. And our recommendation is you don't get tied up at this point into kind of detailed scoring and things, as that's not as valuable at the time of threat modeling, and it takes up a lot more time. So this is something that can be done quickly and can really help you kind of prioritize and rank threats next to each other. When looking at the consequence part of the risk, you want to look at how does this threat affect confidentiality, integrity, and availability of the system. And so before you even start any threat modeling, you can look at your particular system and you could say, how am I affected by this? So in an IT system where you're processing credit card numbers or social security numbers, a loss of confidentiality means you're giving away credit card numbers and social security numbers, and that's often the most critical thing. For an industrial automation and control system, lose confidentiality can be important, but it's usually not the most important. So maybe a complete loss of confidentiality in a system would be medium, and a partial loss might be a low impact, low consequence. But the integrity of the system is much more important. If the integrity is compromised of a control system, then the system may be out of control and may result in a very dangerous situation, which could damage equipment or cause an accident or injure or kill people. So typically for an industrial automation and control system, the integrity part of the system is the most severe consequence. And then availability is also very important in a control system, often because when a system is unavailable, it's a significant loss of revenue. So maybe a complete loss of availability might be high for a given system, but a partial loss might be a medium consequence. So looking at this at the system level is kind of a good way to start. Then when you're looking at each individual threat, you can try to figure out, based on this system and this analysis that you did up front, it makes it a little easier to figure out what the impact is of any individual failure. And then for likelihood, as I mentioned, you want to look at exploitability. How easy is it to exploit a given threat? And some factors you can look at that are shown here. And one is access to the system. So do you have to be local? Do you have to be physically at the system in order for this threat to be achieved? Or can you achieve it from a network attack? So you could be thousands of miles away. Or do you have to be adjacent? Maybe you don't have to be at the site, but if you could take control of another component or system that's on the same network but adjacent to it, then you can carry out the attack. So it's obviously a lot harder to get local physical access to a device in most industrial control systems. So therefore, if the attack can only be carried out locally, the likelihood is lower. Whereas if it can be carried out remotely on a network far away, it's much higher. Authentication is another factor. In order to carry out the attack, can you be a remote anonymous user? So can you be an anonymous user, not even logged into the system to carry out the attack? Or do you have to actually have stolen someone's login to carry out the attack? And then if you did steal a login, is it single factor or multi-factor authentication that's required? Obviously, to get into a multi-factor system, it's even more difficult. So if an attack can only be exploited if you're logged in using that method, then you might say it's lower priority. Access complexity, just what's the overall complexity of the attack? How difficult or easy is it to carry it out? And then target feature distribution. Attacks usually are enabled by specific features or functions that exist in a product. And so if an attack is a weakness in a certain feature, so for example here, maybe you found a vulnerability in downloading firmware to a system, but maybe the majority of the users don't download firmware, and maybe it can be disabled for them. And if it's disabled, then the attack might not be possible. So essentially by disabling features or reducing the attack surface, you can lower the probability of an attack, and that should be considered also in terms of likelihood. So we'll talk briefly here about the security levels of IEC 62443. So these security levels in the standard can be applied to components and to systems, and they're essentially written to describe the level of attack a system can or is designed to withstand. So security level 4 is the highest, where you have an attacker that has sophisticated means, extended resources, specific skills for industrial control systems, or maybe even your specific system, and they have high motivation. So this is the highest level of attacker. We sometimes call this like a nation state type attacker, and they have lots of resources and expertise at their disposal. It's very hard to protect against this type of attacker with such large resources, but there are things you can do to make it more and more difficult for them. At the other end of this spectrum, at SL2, would be an attacker that has simple means, low resources, generic skills. So it's someone that really isn't that sophisticated of an attacker, and they might not be that motivated or have much time to spend on it. So there's certain attacks that are out there they might be able to easily get on the internet and carry out easily, and you might need to be worried about those attacks, but they shouldn't be able to do something really sophisticated like a more sophisticated security level 4 type attacker. And then there's security level 1, which is really not protection against someone intentionally attacking the system or targeting the system. It's what we call casual or coincidental violation. And what we found in analyzing security issues over the years is that oftentimes it's just someone that might be an employee trying to get their job done, and maybe they've bypassed security for one reason or another to try to do something to the system, but they don't have malicious intent. But oftentimes that still causes problems in the system. Maybe they triggered something they weren't supposed to use. So at security level 1, you're just kind of protecting against those types of incidents. And security level 0 essentially means that you don't have any specific requirements. So the stronger the attacker, the stronger of a system you need to defend against such an attacker. So reason why I bring up these security levels is this is often can be used to determine the minimum acceptable risk. If you feel like your system is only designed to protect against security level 1 type issues, then you can just mitigate the highest issues, the most critical issues. But if you're targeting security level 2, then you should also mitigate critical issues. And for security level 3, medium issues also, and security level 4, all issues, because the security level 4 attackers have such resources at their disposal. So this is a guidance. It's not specifically called out in the standard. You can determine your minimal acceptable risk, but this is a way that we would recommend to do it. All right, so now we're going to go through a simple example of how we follow this process, the process that we go through to do threat modeling. And I'm going to hand over to Jeff to kind of pick up from here.
Okay, thanks, Mike. So what we want to do here is, like Mike was saying, we want to come up with a simple model that lets us do some simple threat analysis just to get the principles across, and how we kind of use the ARCHx tool in order to help us manage the information flow. So we'll be using the ARCHx tool to document the example, or at least show parts of the process here. ARCHx itself is a tool that we can do different kinds of an analysis with. It's a tool that was developed here at Exida. So we can do system failure mode effects analysis. We can also do software FMEAs or software HAZOPs, as well as doing the threat modeling. But what we're going to look at today and what we've been discussing is the threat modeling. Again, as Mike said, there are multiple different ways to do the threat modeling. Here we'll use the top-down approach. The reason for doing that in general, as opposed to the bottom-up or the data flow approach, is that you can control the level of depth that you get into, and so you can control the amount of time that is taken. You can decide on what your return on investment is, on how much time you're going to use, what kind of resources from the point of view of people you're going to use. So that lets you use the top-down approach is what we're going to use. So next. So again, Mike had already discussed these. So the first thing we're going to do is create a high-level description of our target of evaluation. And then we'll create a context diagram in ARCHx. So if we go to the next slide, what we'll see is our example here is going to be an embedded device, and it has a REST API server, which is a server that lets you use HTTP protocol or your browser essentially kind of thing to talk back and forth with the embedded device. And in this case, we're going to be able to read and write digital I/O or interact with the Modbus devices themselves. It's a very common thing these days in order to have a REST API server in your industrial control devices. It's an easy way for users to operate the device, and it allows more generic access. But of course, with those two things, it means that you have security issues that you hadn't had before. So the first thing we want to do, again, is create a context diagram, which Mike said is how the device interacts with external entities. And we want to put that into ARCHx as we go along. So it's the next page. Let me show you an overview here of what the ARCHx model looks like. It's essentially a tree model. You'll see there's various colored nodes here. The yellow ones are generic nodes, which are used for organizational purposes. They also contain information such as tags or attributes with values in them. Depending on what kind of expert knowledge that we have loaded into ARCHx, we'll get different arrangements of these nodes with different information associated with each node. That can help you to go through the process, especially if you're new to the process. You can see that we also have blue nodes and pink nodes. The blue nodes are our deviations or vulnerabilities. The pink nodes are our mitigations for particular deviations. So as you can see, we'll go through here and we can see that there's cyber context diagrams, external entities, physical interfaces, logical interfaces, attack paths, user assets, like Mike said, very important for the assets. Then we also have use cases that we are using from the top-down point of view, and we have other things such as actors and other things that we'll discover as we go along. Next. Again, here's our first node that we're going to use, which is the target of evaluation. So what we want to do is attach a context diagram which describes our simple device and its external entities. We want to capture this so that we can have a commonality of discussion when we have a group of people together. One of the issues that you run into a lot of times is that you're going to do your cyber threat analysis, and partway through you realize some people were thinking that we were talking about one configuration of the system. Another group of people was thinking of a different configuration of the system. So one of the things we want to do is come up with this context diagram at the very start in order to kind of nail down what part of the system we're going to talk about and how the system's going to be configured. We can pull this in from various either figures or Visio diagrams and attach them to the particular nodes so that when we create reports later, we'll be able to include these diagrams in the reports so that they can be used for analysis later. So you'll see what we've done is we have a unit name, which is our target of evaluation. We've put in a description, which is the embedded device with the REST API. And some notes are, this is just a simple example for the webinar. Okay, next. So now what we want to do is go into a little more detail. Now that we have a common system that everybody understands, and usually the people that are in this discussion are a facilitator for the cyber threats, the architect who understands the system themselves, maybe some developers, maybe some customer support people, or people who understand the general use cases. And there may be a cybersecurity person in there to also help. Let's go to the next slide. Again, so we sit around and discussed, some use cases as a group, going back and forth, tried to figure out how various people are using the system, how various entities external to the system interact with the system, and we come up with our normal use cases. These are the ones that generically are the ones that were the initial requirements of the system itself. So in our case, we've talked about, someone is using the browser and they read or write the set point, or they read or write the digital I/O, or the set point limits for a particular recipe within a process, manufacturing process. This lets us kind of gather all these together, and what we'll do is use these normal use cases as a basis for discussing the misuse cases and the abuse cases later on. So if we go to the next slide, here are some misuse cases that we would have basically discovered. The person using the browser reads and writes a set point, but it's a non-existent Modbus device. So again, this is a misuse case in that you just inadvertently access device X when X wasn't actually on the system. Maybe you inadvertently try to read the digital output. In other words, the system should have been configured such that reading an output should either cause an error or cause some other kind of flag saying, hey, this is an invalid operation. So that might be a misuse case. In terms of cybersecurity, somebody doing that might be probing to find out if there's different devices on the network, or how the system responds to invalid inputs and so forth. But in this case, we're not looking at it as an abuse case. We're looking at more as a misuse case of somebody just inadvertently tried to read something that wasn't supposed to be read. And the same with setting the set point limits. Somebody inadvertently tries to set the set point limits so that the higher one is lower than the low one. In other words, instead of between 90 and 100, they tried to set it between 190. And again, the same rationale with the one above it is, that can be used also to discover various attributes of the system that you might want to come back later and try and attack. And that, if we can go to the next slide, kind of brings us up with identifying the abuse cases. Again, we're going top down, so we're using the use cases to drive the misuse and abuse cases. And in this case, we're talking about people who are actively attempting to attack the system. They really want to find out information about the system. They want to try and cause the system to go into an unsafe state or into a state where they can control other systems through that system. So in this case, they might try and set the set point value out of bounds for a particular process to cause the process to fail, which would cause issues with their manufacturing process, for instance, or cause failure of a particular piece of equipment. Another kind of abuse case from a different entry point instead of the browser / Ethernet point might be from the digital I/O area. And here we may have a digital input that somebody has spoofed and is varying the input extremely quickly in order to try and get the device driver to operate a very high CPU load, which could cause a problem with our recipes that might be running on the device. Another way as well is through the Modbus interface, and they may actually spoof one of the Modbus devices and cause it to give out-of-bounds responses in order to see what the protocol engine on the device does and see if we can cause the device to fail or cause errors in other outputs based on giving the protocol engine bad input. Another one, which is a very common one back to the Ethernet side of things generally, is a denial of service attack on our network stack. That's one of the easiest ones to create, as well as one of the easier ones to try and mitigate, but it is one that if you're not thinking about it, you may not actually have taken the appropriate action in order to mitigate that particular attack. Go to the next. In this case, we were going to read and write the set point, and what we want to do again is look at the attack path here. You'll see that what we've done here is used one of the generic nodes from ARCHx in order to capture this attack path. And what we can see is we're coming from the browser into the network stack, the REST API server, set point control, and eventually through to the Modbus. As we do this, we've identified a couple of assets in this particular instance that we find very interesting, which is the REST API server and the network stack. As you go through each one of these different use cases, you'll tend to discover different assets until you've kind of got a common core of assets that don't change as you go through different various scenarios, which is what you're trying to get at. In other words, now we can identify our assets and use them as we go further in. So if we go to the next one, the abuse case here is, like I said, the denial of service abuse case. So what we've done is we've done the same thing. We've created a generic node. We've attached a particular attack path that gets us to the denial of service via the network stack. So what we're looking at is the network stack and REST API server. We use our identified assets already and find out, yeah, we've already considered at some point the network stack and the REST API. So we haven't discovered any new assets, but we've now considering a denial of service, taking the browser out and adding in a particular threat agent that is actively attacking our network. If we go to another abuse case here, changing the set point out of bounds, again, we'll use a generic unit node. We'll create an attack path here. We want to set point value out of bounds for the process, again, from the browser through the network stack via the trust boundary. through the REST API server into another trust boundary and into Setpoint control. Again, here now we've discovered a Modbus device that we're interested in from the point of view of being an asset. So we get to the next one. Now, as Mike said, what we want to do is assign risks to the different threats, and we do that by looking at our different attack paths and trying to find out which one causes the highest risk to the particular threat, or lets the threat create the highest risk to a particular set of assets, and then we can assign a risk to that threat. And then again, we want to keep in mind what our minimal acceptable risk is going to be, and then we will eventually mitigate the threats above that minimal acceptable risk. So if we go next slide. In here, what we consider is the abuse case, again, the denial of service one. And you can see we've put it in blue, which, as I mentioned, was a deviation or a vulnerability node. And we were saying, okay, the denial of service against the REST API server, it's a cyber attack. And the description is that we're basically going to flood the network stack with packets. And we want to see how that is handled. What we want to also say is what is the likelihood and severity, or likelihood and consequence, like Mike was saying. So the likelihood is high. It's very, very common to generate denial of services against network stacks. So that's very high, and it's very easy to do. You can get a lot of script kiddie stuff and get you onto and creating different flooding scenarios. The consequence is also high, because if you end up with a denial of service against your network stack, you can end up with a control issue on your device, may lead to failure of the manufacturing process. So that's both a high likelihood, a high consequence. So the risk, if you remember from our risk table, is critical. So the minimal accepted risk in our example here, I think Mike had mentioned we're going to take a medium. That means that we do have to mitigate this particular vulnerability. And in order to mitigate it, there are numerous ways we could do it, but the one that's most often done is to add an external firewall. So adding the external firewall gives us a way to block the flooding of packets to the device, so the packets actually never get to the device. So this means the control algorithm running on the device hasn't been disturbed. And you can see here we can say, okay, add an external firewall, especially blocking port 80 and any other ports that might be needed. And note that this should be used for all our open Ethernet ports. So that's what we want to use here as a mitigation. Okay, the next one. Again, set point out of bounds. Somehow it got set to out of bounds, so that's our deviation. What we find is that if we set it outside of bounds, after discussing it with the members of the team, we find out the process might go out of control. So we say, let's consider this. What's the likelihood and severity? The likelihood's kind of medium. That's what people decided. That yeah, you could set it out of bounds, but maybe not really. But the consequence would be pretty high if there was some way you could get it to go out of bounds. So again, when we look at our matrix, we would find out that a medium likelihood, high consequence gives us a high risk. So therefore, again, since we have to mitigate from medium up, we're going to have to mitigate this. So we create another node within ARCHx that's our mitigation node, and that lets us decide how we can mitigate the out of bounds process. And what we've decided is ensure there's checks on the set point range values to keep it in range. Now there's 3 different places we could do it. If we looked, when we look back at the threat path, there was the browser, set point control, or the Modbus device itself. You don't want to do this check in the browser itself because, as we discussed this particular attack, the browser is not even involved. So in general, you want to get it as close to the source as possible, which in this case is set point control. So you probably want to go ahead and make sure that the set point control has been designed to keep the values of requested set point changes within a range based on the particular process that is being used. Okay, next. And so, in conclusion, what we've decided is that there are different approaches, like Mike said, that can be taken to threat modeling. We can do top up, bottom down. We can look at assets, we can look at threats, we can look at vulnerabilities and come from any of those particular angles. The approaches could vary by different projects. You could even have, one day, looking at top down, and another time that you meet looking at the bottom up view. These would give you the best overall coverage of issues in your device. So just to restate what we did, we identified some use cases. We used those to identify some misuse cases and abuse cases. We looked at some attack paths and assets. You saw that we could put them into ARCHx using the different various nodes, and we then identified the threats that were there and gave them some risks. Okay. Other ways, again, that you would do it is to look at physical interfaces, or from an assets point of view. You can use the different models. Mike had talked about the CIA model. There's also the STRIDE model. And any of those can be used to determine whether, here's an attack path, here's a place to take a look, and also decide, how it is you want to consider the device that you're looking at. Okay. Again, we can use ARCHx itself, allows you to configure the nodes however you want to configure the nodes. It lets you create the linkages between the nodes to associate different mitigations with different vulnerabilities or different deviations. It collects and lets you see common threats and attack paths. The various approaches could be linked together. When you generate your reports, you'll find out, here's all my assets, here's all the mitigations that are done against various vulnerabilities so that I can get to my different assets. You can create kinds of reports along those lines. And again, it kind of uses the idea of a tree view in order to organize all of the different information that you're going to use and go back and forth into it. So, next. Okay. Mike.
All right, so thanks, Jeff. If you have any questions at this point, feel free to use the question part of the webinar to send them our way, and we'll try to go through any questions. In the meantime, what I show here is some of the upcoming training sessions we have within our exida Academy in the next few months for the rest of the year. So the first question I have is, when in the life cycle should a threat model be done? And so that's a very good question. I don't think we discussed that. And essentially, threat modeling should be done early in the process, but you should at least define the architecture of your system. Obviously, from some of the key parts is you really need to have that context model ready to go, where you've kind of shown what the system is supposed to do, what its functions are, what its interfaces are, and then the overall architectural design needs to be done. Once that's the case, you really don't have to have started or completed much of the actual implementation of the system to start identifying threats. And we recommend doing that early, as soon as possible after that architecture has been defined. Because as you define threats, you're going to come up with mitigations, and the earlier in the life cycle you come up with them, the easier it is to include it in the design that you go through. So that's the first question that I have. I do have another question here about, is it possible to get a trial version of the ARCHx tool? And I believe that is possible to get a trial version. So I'll show you. We have, over here at the end, our email addresses are shown here. So send an email to either me or Jeff after the meeting if you're interested in getting a trial version, and then we'll kind of work with you to try to set that up and and get that to you. All right. So next question I have is the threat model required for all security level of a product? And the answer to that is yes. All security levels require a threat model. Obviously, at the lower security levels, you might not have to be concerned about as many threats. If you identify a threat that's, takes really a lot of knowledge and resources and such for a system that you're only designing for security level 1, you can say that threat is below your risk threshold. You don't have to worry about it. But even at security level 1, there's going to be threats that you're going to want to consider and be concerned with. And so, yeah, you should include that for all security levels. All right, the last question I see here is, can threat modeling be done in parallel with a FMEA or a software HAZOP? And the answer to that question is yes. One of the reasons why we included threat modeling in this ARCHx tool is people have been using this tool for doing software HAZOP, software FMEA, system FMEA type work. And in doing that work, you define a lot of the different components of the system. You define the context diagram. So you really do define a lot of the same types of parts of the system that you would need to do a threat model and a threat analysis. And so we recommend that that's done in parallel or shortly, after you create that. If you're using this tool for doing both, it makes a lot of sense because you've defined those common components, and then you can go off and kind of have two different teams kind of work in parallel, or the same team work on it one after the other. Whatever makes the most sense. Last question is, does functional safety, for example, IEC 61508, 61511 require threat modeling? And so 61508 and 61511 do require that a threat analysis be done to determine if there's any viable threats to a system. And if there if you do determine there's viable threats, then you need to take some action to mitigate those threats. It doesn't get into the level of detail of 62443 that defines more details about what needs to be included in the threat model and such. So in 61508, it just defines at a very high level that yes, you do need to do some sort of threat analysis and determine if security threats are something that you need to be concerned with, that could lead to dangerous failures. And then if so, you must include those in your risk analysis and put in steps to mitigate those threats. So that was also a very good question. All right, so I don't see any more questions, so I want to thank everyone for joining the call, joining the webinar. And as I said, our email addresses are here. If you have any more specific questions after this, feel free to follow up. And if you also have any questions about cybersecurity certification in general, that's really a lot of main area that Jeff and I work on, so feel free to send that out as well. All right, thank you very much for your time, everyone, and I hope you enjoyed this webinar.